Kelvin superheat control. Have y'all heard of this before? Any of you ever heard of it before? It's electronic expansion valve.
Yeah, there was a fella in here, our last RSES meeting, wasn't it?
Yeah, yes. Well, good. I'm gonna count on you to tell me, because I gotta do it Thursday night at RCS so that I won't duplicate too much of what he did. But we're gonna be talking about this controller, and I'm like you guys. I'm a technician. I'm a refrigeration technician, and we work on supermarket refrigeration. And the reason we have this right here, I'm not a salesperson for spoiling. I do like their product, but this is what our guys see in the field a lot of. Did I get that mouse off the screen there?
Yeah,
Okay.
you're fine.
This is what our guys see. And David actually helped me build this demonstrator right here so that our guys could come up to this system and we could talk about it and plug into it and say, here's how you go through the different parameters of this particular controller right here. And that's what we're going to be talking about tonight. And I think we're going to have to do a battery change here, David.
All right.
I'm pretty sure I got some batteries.
What side?
There's some in this box right over here. Triple A's. What we're going to talk about is how this relates to the refrigeration field, but it also relates to a lot of HVAC field as well. Now I want y'all to give me a kind of an idea of where you guys are in your level of training. Where are y'all? Okay, that's what y'all tell me. Just kind of give me some ideas. How many of you are through the basic course already? Okay. How many are into heat pumps? Electricity? Okay. Y'all got a good grasp and understanding of that? Okay, good. What we're going to talk about is how to access the controller. We're going to talk about some of the basic setup parameters of the controller. We're going to talk about some of the troubleshooting. And then y'all going to have some time for hands-on. Tonight I won't have time for hands-on here, but I'm going to leave this demonstrator with y'all for about 3 weeks. Because I understand y'all be here the rest of the week, this week. If you're here, you're welcome to work with it. There'll be an instruction sheet that talks about setting it up. If you tear it up, you ain't going to tear nothing up. We can't fix. We can fix it, so don't worry about that. But it's here for you to work with and set up and walk up to and plug into, change the superheat, change the parameters. That's the only way you're going to be able to work with it. I just stand up here and talk about it all night long. And the only thing I hope to do is just get a few things in your mind to where you can pull this little instruction sheet, this little instruction card out right here and go through the parameters and wire it up and set it up where you can do that on your own. I can talk to the cows come home. It'll never get in your brain until you come over here and you start twisting on knobs. You know, if you let the smoke out of it, do not worry. I got another one at the shop we can put on there, okay? So don't worry about fixing. Now let's go back to the basic refrigeration cycle just so we can cover that. Remember that the compressor is the pump of the system, the heart of the system. It takes high pressure, low pressure refrigerant and converts it to high pressure refrigerant. Operates by screws, scroll, or pistons. Y'all know what I'm talking about when I say that. It comes out of high pressure vapor, goes into the condenser, it rejects its heat, goes to the metering device where it converts it to a low pressure liquid and vapor mixture, and it goes to the evaporator and absorbs heat there completely until it is 100% vapor. It's supposed to be 100% vapor. When it comes out, it comes back to the compressor as a low pressure. Okay? So, you got two distinct sides, the high and the low side. The compressor divides it and the metering device divides it. The metering device needs to make sure that there's no liquid coming back to this compressor. That's the main purpose of controlling superheat, is to make sure that there's no liquid coming back to the compressor because we don't want to damage that. Now think about this. That refrigerant is circulating through there. Here it's rejecting heat. Here it's absorbing heat. I've always thought of that refrigerant as a sponge. If you had two buckets of water, one over here and an empty container right here, and you took a sponge, a dry sponge, and put it in the water, brought it over here and squeezed it out, that's what that refrigerant is. All it is a heat sponge. And if you think of that refrigerant as a heat sponge and you kind of get an idea of what's happening inside that system. Remember the definition for refrigeration or air conditioning. It's the process of taking heat where it's objectionable and placing it somewhere where it's not objectionable. That was a mouthful, wasn't it? Y'all got that one remembered, don't you? That's really what it is, though. All we are is we're moving heat. We're moving heat. If we're wanting to be cooler in this room, we move the heat from this room somewhere else, typically outside. It's gonna be cold tonight, isn't it? So you ain't gonna be wanting to take no heat out of the room, are you? You're gonna be adding. How many of y'all have heat pumps at home? Got a couple. I have a heat pump at my house. I have a heat pump at my house. So basically tonight, unless your wife gets a hold of the thermostat and gets the electric heat turned up there, you're going to be taking heat from outside and moving it inside. And you say, well, how's that possible? Well, there's heat always above minus 460 degrees, right? Y'all learned that in the basics. I'm just kind of refreshing your memory of this stuff. There's always heat above minus 460 degrees Fahrenheit. So you're taking heat from outside. Now, today's heat pumps are pretty good at wringing heat out of the air down to 15, 20, 10 degrees, aren't they? I told this story this morning. I have a new heat pump installed. It's a Carrier. It's called Infinity. You ever heard of that one? It's a 3-ton Carrier Infinity. It's a variable speed compressor, variable speed fan. Now, I have this little thing on the wall. They call it interface. I call them thermostats, but they call them interfaces now. There's somebody out there.
Yeah,
Then come on in here.
Yeah.
You ain't hurt my feelings none. Come on in here.
Moses.
Come on. You come on in. We're waiting for you.
No, man. Gotta drop the kids off, man. Can't bring the kids.
That's the way it goes, isn't it? But you know, they used to have this thing on the wall, and they called it a thermostat. And when I was coming along, people would get the mercury out of it. It had a little mercury bulb in them. Y'all don't see that much anymore, do you? There's not that mercury bulb in there. But now they got what they call an interface. And as Jerry Clower says, you can just kind of go up that thing and jig the button and make it do whatever you want to. Now, the people who installed my system, they did not know that I was a refrigeration guy, and they didn't tell me how to get into the service mode of that heat pump, but I done got it figured out. You know, you kind of go through there, and I got my granddaughter to help me out, put some codes in there, and I got in there. So there's a way you can lock it strip heat out, okay? So I lock that strip heat out. You remember last winter when it was down to 6, 7, 8 degrees for about 3 nights in a row, 2 or 3 nights in a row. Remember how cold it was? Mm-hmm. Well, my wife did not know this, but I went in there and I locked my strip heat out. In my house, the coldest it got with heat pump only was 68 degrees. Now that was phenomenal. I didn't use any strip heat, and I am not joking. My first system, I built my house in 1985, and it's not what you call a tightly sealed house. I don't have any floor insulation. My house is one of the houses you see on TV. You stand next to the receptacle and you can feel the air coming out of the socket, you know. I did put new windows on the house about 10 years ago, so that helps a little bit. But I don't have what's called a tightly sealed house. Matter of fact, the heat pump folks would say, you need to seal this house up before we put a heat pump in it. But anyway, we put a heat pump in it. It did a great job of cooling. Part of the performance of that heat pump came from this expansion valve, or one just like it. That they say that's one of the most dramatic increases that they have in efficiency. Now, being able to extract heat out of the air is the operation of this valve right here. And it's pretty neat. You can sit there on the wall, just like you can this thing right here, and look at it and see what the position of it is, see what the coil temperature is. A lot of different parameters you can look at, but it is really neat. But anyway, so that thing was able to extract heat out of the outside air and keep my house warm. And that's pretty warm. 68 degrees, as cold as we would have it, and as hard as the wind was blowing. So I thought that was pretty phenomenal. My power bill dropped by at least 2/3 for the wintertime. I'm not joking. And I was one of those people, I said, I ain't never getting no high efficiency unit. It's a waste of money. But it actually worked out pretty good. Okay, any questions on the refrigeration cycle there? Before we move on, this is just kind of refresher, redundancy kind of stuff. Okay, superheat. The reason we need superheat is because we have to be able to make sure that there's no refrigerant coming back to that compressor. As a matter of fact, when you're playing with this thing over the course of the next few weeks, I want you to literally cut the fan off, let it flood back, and you'll see, even though it's got this big accumulator on it right here, for the size of this thing, that refrigerant will still flood back to this compressor. So there's no 100% way of saying for sure that you're not getting refrigerant back, so it's imperative that we control superheat. Number one, to protect the compressor. Number two, to improve the efficiency on the coil, because we maximize the use of the coil. Because look what happens right here, and this is R22, and I know we don't use that anymore, but it comes out of the expansion valve right here, and it's a mixture of liquid, low pressure liquid and refrigerant. It's 58.5 pounds right there, which is, they say, I'm going to take them at their word, 33 degrees. Do you know what I'm talking about when I say the saturated suction temperature is 33 degrees on that coil right there? Does everybody understand that? Okay. Now, if you don't feel bad. Because I'll tell you what, going through the course of time of life, it takes me about 10 laps around the track to get something, okay? Somebody will tell me something, and I'll be sitting in one of these seminars, and I'll say, I got it, I got it. I'll get home at night, and I'll write it down, and I'll say, I got it, I got it. I go to bed at night, I'll get up in the morning, the next morning I'll say, I ain't got it no more. It's gone, you know, went somewhere. But there's always a correlation between a refrigerant, which is a substance that absorbs heat, and its temperature / pressure, okay? One of the guys this morning gave an example of water, and I'll start off with that because that makes it pretty easy. Water boils at what temperature? 212 degrees at 0 psi. On top of Mount Everest, what does it boil at? About 180 something, isn't it? It is. It is. I promise you, anybody that's ever done any hiking and has ever gone to the mountains, y'all know what Roman noodles are, don't you? Everybody know it. Everybody that's been to college or school knows what Roman noodles are. I know what they are too. There's them little noodles, you know, you pour boiling water on them, you boil them, and then they get soft and you suck them down. You know, they're supposed to provide energy for you, but the reality of it is they're not very tasty. Well, if you boil them up at altitude, if you go camping or something in real high altitude, then you'll see that it takes longer to cook them noodles, potatoes, or anything else. That's because the temperature of that water is not as high. It's because of the temperature. Now, it says on this chart right here that for R22, that at 40 degrees right there, that 68.6 pounds is the pressure will be at. I'm here to tell you that if I had a drum of R22 and I hooked this gauge to it right here, and that drum had been sitting in it, and I read the pressure off this gauge, I could tell you what the temperature was in that refrigerant. Everybody believe me on that? Okay. That is the saturation temperature. It occurs in two places. It occurs in the evaporator right here and the condenser. Okay? Evaporator, you'll hear people say we got a 40 degree saturated suction temperature. You'll hear people say I got a 110 degree condensing temperature. Okay? Y'all have heard those terms before. That's what they mean. They mean that's what the temperature is. So you take that temperature and convert it to a particular pressure. That saturation occurs at two places in the system. Okay? So, that happens with any refrigerant that we have. That works with any refrigerant we have. So, we take this refrigerant right here, this vapor and liquid, and we boil it off. Now, that coil temperature is going to be what? What's that coil temperature right there? At 58.5 pounds. 33 degrees. It's right there in those letters, right there. Now, I know you can't read that temperature chart, but we're just assuming that it's real and it's correct right there. Oh, the reason I got this out, this is, have you guys ever seen or heard of this app? This is a app from Bitzer. And you can go down to Bitzer and you can download this app. DuPont's got one. I think Genetron's got one. But basically, you can look at every refrigerant that you want and download that app. It's a temperature pressure chart. And let me tell you why that's good, why I think it's good. It's good for me anyway. I can take like this 407A right here, and I can look at the temperature pressure, and it kind of brings me to 3 or 4 different readings right there. When I look at this chart right here, this thing right here, this big old chart, I don't know about y'all, I get all discombobulated. Even when I look at that chart right there, if I don't have two of them, one to kind of hold the line with, you know. Let me just see yours right there. I kind of got to get it like this, and I got to have one right there to hold it like that, and then I got to stick my finger over here and hold it back here where I can see, or put my glasses on. So this kind of, you know, it's better than nothing, but I get kind of discombobulated when I look at it. So this thing right here allows me to focus in on where I want to be, and all I got to do is just put my finger right there and go to the temperature or pressure that I want. Because with refrigerant, the temperature or pressure always correlates. That's called, that was supposed to be a question. So when the temperature and pressure correlate together, that's called saturation. Saturation, okay? They're in equilibrium, vapor and liquid in the same state, okay, at the same temperature. All right. Heat that's added to or above that saturation temperature is called superheat. Thank you, superheat. Heat that's added above that is called superheat. So, we know we have a 33-degree saturation temperature. So, we know that we have a 40-degree line right there. We know 40 minus 33 is equal to 7, that we have 7 degrees superheat, okay? Now that's all done with just a plain mechanical valve right there. We're going to do the same thing, but we're going to be doing it with an electronic valve, electronic controller and a valve, okay? All right. Any questions on this? Okay. To talk about controllers, now this controller is a non-configurable controller, okay? What that means is that it's set up, it's predetermined what it's going to do, and there are a few parameters that you can set in there. You can set what the superheat you want it to be, you can set certain switches, you can set certain things, okay? But it's a pre-configured controller, okay? This is a configurable controller right here. I'm going to pass this around. You can basically configure this controller to do anything you want it to do. Alright? If you can imagine it in your mind, and you have a reference input and an output, i.e. a temperature, a light meter, a pressure, and an output, a valve, a water valve that you want to control, a refrigerant valve, an expansion valve, whatever it is, and you can conceive in your mind what you want it to do, you can make this thing do it. But you got a program to do it. I'm going to pass this around. This one's configurable, and this one's not. Okay? But it's important that you kind of know how this configurable controller works, so you can understand some of the processes in this controller right here. Okay? So I'm going to talk to you just a minute about the inputs, some basic control things, the inputs of the controller, the internal working part of the controller, some control terms that you need to know, and then the outputs, kind of in that order, okay? So, inputs on this particular controller, you can configure them to whatever you want. This one you can. The functions have to be programmed by a laptop with a software on that controller right there. On this one, all you need is this little device right here. This little device right here will let you put your parameters in here that you need to put in. You need to provide the AC and DC power for this one right here. This one's powered up by 24 volts AC right there. And that one requires a lot of programming time. Once you get used to programming, it's not a long time. But you got to learn the software, you got to learn the program, you got to learn how to write the code. And to program that device right there, you have to go to, I've been to California at least 5 or 6 classes on that one, and I'm not even a controls guru. You know, I'm just kind of a hit or miss kind of guy. We got guys that really know how to do that thing, but you've got to spend some time learning how to do it. Just right here, in one evening, you can make it work. One evening. I wonder if that's my machine right here, a hammer drill over there. I didn't know what's going on. Okay, this right here is an input, and This is an input right here. I'm going to pass it around. And it's one of the things that this controller will look at, okay? And this is a pressure transducer. I call it a transducer. They operate a lot of different ways, but this is one particular way that it works. This is picture this as just a flat piece of metal, a disc, okay? And it has this material on there, and when it flexes, it changes resistance. Y'all know what resistance is, right? It's an opposition to flow of current, right? So basically, if you have your ohm meter on there and the resistance goes up, the ohm value goes up, right? Okay, it looks something like this inside. You basically have a pressure point where you come in. You have that strain gauge right there, right here, that presses against that. The pressure comes in, and then there's some electronic stuff right in here that actually converts that to something meaningful to that controller. So what happens is this can change. This little piece of material right here can change. I'm not pointing this right. Can actually change resistance. It can change capacitance, or it can be something known as a piezoelectric. Have y'all heard of that before? Piezoelectric is a substance that when you put pressure on it, it generates voltage. You've all seen it, I guarantee you. You got one of them gas grills that you punch that red button on that don't have a battery, and you hear it go click, click, click. That's what that is. That's a piezoelectric spark. And what it's doing, a little rod's hitting that thing, and it's making a spark, okay? And there's a substance in there like a rock, crystal I call it, and it hits that and it generates a high volt that makes a spark to ground. It's just a little minute spark. But anyway, a piezoelectric material, actually when pressure's put on it, it creates a change in voltage, okay? So that's the pressure gauge. Temperature input called thermistors. Now that's a little wafer looking thermistor, and that says PTC, that means positive temperature coefficient, okay? Now it's back to the resistance again. What that means, PTC means as the temperature goes up, the resistance goes up. If that was NTC right there, as the temperature went up, the resistance would go down. That's all it means right there. Now, that thing in its state right there is basically useful for something like on that board over there that I've been passing around, but it's not much use in the field. That thing wouldn't last very long in a refrigeration case, would it? Or in a refrigeration system, or in somebody's evaporator coil. That thing would just get tore all to pieces. I think there might be a couple of them on that device back there if you look at it. So in the field we have something that's encapsulated, a sensor, a thermistor that's encapsulated in some kind of brass or stainless steel, and it looks something like this. Now there's different ones. This just happens to be one of them right here. And it's encapsulated for strength, so it'll be strength and durable. Now, one thing about the thermistor, this is what we have here, you see it has a very distinctive curve. And I'm only telling you this so that you'll know the difference between the two of them. If somebody ever asks you the question so you can like act like you know that you know what you're talking about, you know, you can carry on a conversation, say, yeah, I understand what an RTD is. RTD stands for resistive temperature detector, okay? And basically, you can see it changes it. And these are units of resistance right here, 0 to 7.25. And this is temperature from -20 to 100. You can see that our thermistor has a very sharp curve on it, okay? Now, the controller is programmed to look at that curve. The RTD has a very shallow curve. Typically, they use these on scientific equipment, and they're very accurate within a very short range, okay? So there's a purpose for them. Now, the cost of them is much higher. It's about 10 to 1. So you might pay 15 bucks for that little sensor back there, and an RTD would be 115, 120 bucks. So that can be a lot higher than a thermistor is. Any questions about inputs? Okay. So we're going to talk about some control terms. Now, I don't want none of you to go into low blood sugar panic or convulsions, or you have to double up on your blood pressure medicine, because these terms right here, remember I said a minute ago, you're going to have to go back around the track several times. We're going to talk about some terms here. They're called droop, deadband, throttling range, proportional gain, open and closed control loops, and PIDs, okay? So we're going to talk about those things. Very simply. Droop. Droop is the difference between the temperature that you want it set for, let's say it's 72 degrees, and what it's maintaining. That's what droop is. And you're going to see how this plays in the control loop in just a second. But droop is the difference between those two. In other words, I got it set for 73 degrees, but it's maintaining 72 degrees, and if the load remains constant, it stays right there. That is the droop, okay? The deadband is a period of time when you go from heating to cooling. You see, if you follow it transitionally right there, it goes up. There's a point where it can kind of be like toggling back and forth between heating and cooling. You don't want that to happen. That wastes energy. So they create a deadband, and that is a period or temperature where that nothing happens. There's zero heating or zero cooling. Okay, so imagine you have a cooling valve and a heating valve, and you come up, your heating valve shows, it begins to close off, it goes to zero, it goes through this deadband period, then your cooling valve begins to open as the temperature comes up. The deadband typically keeps that from toggling back and forth between heating and cooling, okay? And that's an energy saving function right there. Throttling range. Throttling range basically means that for a period of input, or a time or a function of input that is proportional, it goes from 0% to 100%, and that can be from 1 degree, 5 degrees, or 10 degrees. And let me explain that. If the throttling range is 1 degree, it starts at 1 degree, it's 0. We use cooling as this application. The cooling valve will be 0. It gets to that 1 degree, 1.1 degree, it'll be 10% open. 1.2 degrees, it will be 20% open, and so on and so forth. They'll go right on up the range just like that. Well, that 1 degree at 2 degrees, or 1 degree completely there, it'll be 100% open. That means your throttling range is 1 degree. Now, if your throttling range was 10 degrees, let's say it started at 72, and it had a throttling range of 10 degrees. At 82, that cooling valve would be fully open. You understand that concept? Okay. You sure you understand the concept? Because I'm prone to lousing stuff up occasionally, not saying it just right. Okay? You got that? All right. Proportional gain. Proportional gain means that for every unit of input, it relates to a certain unit of output. If proportional gain is 1 to 1, that means for every unit of input, the output is 1 unit, okay? And we'll see that here in just a minute, a little closer, okay? But just remember it's proportional. If it clicks up, if it's 1 to 10, it goes up 1 here, it's going to go up 10 here. If it goes up 2, it's going to go up 20, okay? It's always proportional. A control loop that has no feedback to it, okay? Some examples of these are, let's say we have a bucket, a 5-gallon bucket that we want to fill up with water. Or I'll tell you a better one. Have you ever seen a horse tray, a big trough that they water horses in or cows in? So you go out there and you just go out there and say, okay, I want to fill this watering trough up. So you go up to the valve and you just turn it on and just leave it running and you go off. Okay, that is effectively a open control loop. You turn the valve on, it's filling the tank up, but that's all it's doing. I was going to say on this one right here, a tractor. How many of y'all driven a tractor? Okay, most of y'all, like that more y'all know what a tractor is. I was going to use the analogy of a tractor, you know, where you set the throttle position on the tractor, or you set the power and you leave it there and there's no feedback mechanism. I know I see a couple mechanics in here, I know there's a governor and whatnot, but just for the sake of this explanation here, take it for a second, you just set it and leave it there. But there's no feedback on that. So you just set an accelerator pedal at a certain position and you hold it there, regardless of speed or anything else. The next one would be where you took this controller right here and you said, I want to open this valve up to 70%. You just open it. I'm going to fill over here and you can do that. And I'm going to position this valve to 70%. And you leave it at 70%. and nothing else. It's just running. The valves that sit at 70%, it's 70% open. Those are open control loops. Closed control loops. Go back to the water tank analogy. We have our bucket there. Well, we don't want it overflowing. We don't want the water trough to overflow, so we put us a float on there. On that water valve, we put a float and it comes up and it cuts the water off when it reaches a certain level. So that now has feedback, doesn't it? What's the feedback? The float's the feedback, isn't it? Yeah. Cruise control on an automobile. Okay? As Jerry Clower says again, you're driving down the road, you just get 60 miles an hour, or hardly 55 miles an hour, and you hit the button. You juke that button on your steering wheel and it holds it right there at 55 miles an hour. And what's the feedback on that? It's getting feedback from where? Huh? Well, yeah, but I mean, it's looking at the speedometer. Yes, you're right. It may be holding some parameter, but it's looking at speed. You know, you're trying to control speed. So yes, you got some feedback there that's controlling. So
86 miles per hour.
David and I took a trip a while back, and I told him I have this GMC diesel truck, and I have the chip set in it where I might have chipped it up just a little bit. You know, you drive trucks. We got the truck drivers in here, okay. What kind you got?
01 Duramax.
Huh?
01 Duramax.
Okay, I got a Duramax too. I got it, and my grandson's got one of them Ford F250s. What do they call them? Yeah, I told him, let's hook that thing up, son, and I'll pull him all over. I'll drag him all over the parking lot. Maybe not. He got a pretty good truck. But anyway, so Dave and I take a little trip, and I like to drive slow and easy. Generally about 97 miles an hour where I like to drive. And I had the chip set where that's as fast as I can go in order to keep me from getting one of them excessive speeder tickets, you know, just in case. So that's what he's making a joke about.
Keep us from going back to the future.
But I tell you what, if we're ever in North Carolina or South Carolina, and we got like a group of people riding back, everybody wants to ride back with me, because we're gonna get back first. So they want to ride back with me, and they want to get home in a hurry.
Just close your eyes, everything's fine.
Close your eyes, turn the radio on. That's right.
Hold on.
Hold on. Now, the next one is a PID. Have y'all heard this term before, PID? Proportional Integral Derivative. And basically, I need to tell y'all something. This thing really, it's a math function device. That's really what it is. And when you go to the School of Higher Learning on these PIDs or any kind of control system, you'll find out that these things just basically are working algebra and other math functions in this device right here to come up with some result that we can utilize out here in the world. Now, do not ask me, because I do not know how the P works and the I works and the D works, but I do know that you can go look at those and there's an algebraic function for each one of those. And it's really a function of math. Now there are people that study this and know this and that are good at it, but I'm not one of them. But I can tell you some things as to how they operate so you can have an understanding of what they do. Basically, you have some set point that comes into a summing device, and it's also looking at the process, and it works on an error, okay? It sees an error. That's all it knows. All it knows is we're not where we need to be. We're not where we need to be. Now, I don't care if we're talking about bowling pins. I don't care if we're talking about boxes coming down a conveyor. I don't care if we're talking about refrigeration, valves, speed of a vehicle, or whatever. PIDs are utilized everywhere in life. And it takes those things and uses these functions right here and takes them back to a process. Now, believe it or not, a PID, every one of us knows what a mechanical PID is, and it's in their commode. And it really is. You have the same function. You have a proportional valve that lets water into the tank. And this example right here is taking a tank of water, and you have a variable flow control valve right there. And you have a float with a forkum on it right there that's movable. That is the PID function of this, okay, of this device. So it is a mechanical device. And actually, PIDs were in use long before electronics even electricity was ever discovered. The first one, I think I was telling David that I can come back and account to, is on the sailing ships where they invented actually a course holding device. And it took the pressure of the vessel on the sail and it connected it to the rudder, and sensed the pressure on the rudder, and there was a spring, an offset spring under the ship's hull that allowed it to hold its course or track its course. That was the first time that I can come up with that a PID was ever used in a device. That basically was to set the course of a ship for a specific course and hold it on that course regardless of how the wind shifted or how the currents went or various other things. So I thought that was pretty unique when I began studying about these things. Now the P part, the proportional part, is the ratio of change to input to output. The greater the proportional value, the greater the output. 1 to 1 has less effect than 1 to 10. Okay? I feel the same way. I'm just about to go to sleep up here myself. Y'all need to stretch around a minute. Y'all want to break?
Let's
Let's take a break. Y'all want to take a break for a second? Let's go walk around.